Good day and welcome to our class. Today we shall be talking about eigenvalues and eigenvector. But before then, we need to have known determinant of a matrix, which I believe you have known. But let us just quickly go about it. Let's consider 2 by 2 matrix A, B, C, D. If they say that determinant of this matrix is AD minus BC, that is A D minus BC. Let's say this is matrix A equal to this. We normally write determinant like this. We put two strokes like this. It is AD minus BC. That is this diagonal, multiplication of this diagonal minus this diagonal. For instance, let's assume that we have matrix A to be 3, 4, 1, 2. Determinant is simply multiplication of this diagonal. That is 3 times 2 minus 4 times 1. So this is 6 minus 4. Our answer is 2. So that is the determinant. So it's very easy to do determinant of 2 by 2. We just multiply this diagonal. Let's take another example. Let's say we have another example here. 3 minus 2, 4 and 5. So to find the determinant of this matrix, we write this means determinant, or we can just write it like this, bar this. Just multiply the two. 3 times 5, this is 15. Minus, as usual, we have to put minus from the formula. Then we multiply these two. This is minus 2 here. So minus 2 times 4, that is minus 8. So in this case, we have double minus in the middle, so it will become plus. Finally, our answer there is 23. So that means 23 is the determinant. More interesting one is determinant of 3 by 3 matrix. Let's say we have 3, 4, 5, 1, 2, 1, 1, 4, 3. Let's assume that we want to find the determinant of this matrix. If it is 3 by 3, how do we find the determinant? We apply what we call Laplace rule, and this is it. We take this leading coefficient 3, 4, 5, the first 3. We write it like this: 3. We put this 2 by 2 matrix. Also, we put 4. We put another matrix here, and the last one is 5. We put another matrix. But some things will be before those numbers. Here we put plus, minus, and plus. Plus, minus, plus. If it is this one you want to pick, if it is 1, 2, 1 that we want to take as the leading coefficient, since this one is plus, definitely this one will be minus. So it will be minus, plus, minus. So this place will be plus, minus, plus. But we have taken this, so it will be plus, minus, plus. Now, after you have done that, you put 2 by 2 matrix. Now, what are we going to put inside these empty spaces? For this 3, for this coefficient 3, I will cancel out everything in front of 3 and everything beneath it. I will cancel. Then I will write the remaining matrix. If I cancel it, you will see that we have 2, 1, 4, 3. This is 2, 1, 4, 3. If we go to 4, I will cancel everything beneath it, everything at the front, at the back. What we are going to have left is 1, 1, 1, 3. 1, 1, 1, 3. And finally, which is 5. I will cancel out all this. I will cancel all this. What I will have left is 1, 2, 1, 4. 1, 2, 1, 4. So remember, this is how you are being taught. Now, I will now apply what is here to this. Starting from 2 times 3, 6 minus 4 times 1, which is 4. Minus 4 into this one is 3 times 1, 3. Minus 1 times 1, 1. Plus 5 into this is 4 times 1. This is 4 minus 2 times 1, that is 2. So our answer is 3 into this is 2 minus 4 into this is 2 as well, plus 5 into this is 2. So this will give me 6 minus 8 plus 10. And that is 6 minus 8 is minus 2 plus 10. That is 8. So that means 8 is the value of this determinant. So let's consider another determinant before we move to eigenvalues and eigenvector. Let's assume that we want to find this determinant. 3 minus 2, 1, 2 minus 4, 2, 1, 1 minus 3. Let's assume that we want to find this determinant. As usual, I'll first take this one, minus 3. What is there is 3. I'll put this. I'll take this one, which is minus 2. I'll take this one, which is which is ordinary 1 that is there. Now, after that, you know, I will normally say this is plus, minus, plus. So let us now put those plus, minus, plus. This is plus, this is minus, this is plus. But here there is double minus here. It will make this place to be plus. Now, we now insert all these matrices. Starting from 3, I will cancel out everything in front of 3, everything under it. What I'm going to have left will be minus 4, 2, 1, 3. Minus 4, 2, 1, minus 3. I'll come to this one too. I'll cancel out everything like this. I'll cancel this. What I'm going to have left is 2, 2, 1, minus 3. 2, 2, 1, minus 3. And finally, for this, I'll cancel this and I'll cancel this. What we have left is 2 minus 4, 1, 1. 2 minus 4, 1, 1. So this is 3 into, if you find the determinant, minus 4 times minus 3, that should be plus 12. Then minus 2 times 1, 2. Plus 2 into 2 times minus 3. That is minus 6. Then minus 2 times 1, 2. Plus 1 into 2 times 1, 2. Minus 4 times minus 1, minus 4. But there is double minus here, so we are going to put, it will become plus. So this will be 3 into 10, 12 minus 2. Plus 2 into minus 2 minus 6. That is minus 8. Plus 1 into 2 plus 4. That is 6. So this will give me 30 minus 16 plus 6. And 30 minus 16 plus 6 should give me 20. So in that case, 20 is the value of this determinant. Now let us now move to eigenvalues and eigenvector. Consider these definitions. The first one, characteristics matrix. Let A be a square matrix. This is a square matrix. This expression A minus lambda I, we call it the characteristics matrix of matrix A, where this lambda is a scalar, that is a number, it's a constant. That is the meaning. So this expression is what we call characteristics matrix A minus lambda I. So for instance, this is matrix A here. Then A minus lambda I will now be, this is our A. This is how to write ordinary lambda. This is how to write lambda I. Lambda 0, 0 lambda. So what we are saying is that A minus lambda I will just become subtracting lambda from this diagonal. That is the meaning of A minus lambda I. That is, the matrix will just be A minus lambda, B minus lambda. So for instance, if we have, let's say we have 3, 4, 4, 9 as matrix A, then A minus lambda I will just be subtracting lambda from this diagonal. It will be 3 minus lambda, 9 minus lambda, the rest will stay. And if it is 3 by 3, it will go on that diagonal. So that is characteristics matrix. But if they now say that characteristics polynomial, so the determinant of the characteristics matrix is called the characteristics polynomial. This matrix we get here, if you now find the determinant using the method we just finished, you find the determinant, anything we get, any expression we get is what we call characteristic polynomial. polynomial. You can see example here. So it will now lead us to what we call eigenvalue. Now, when it leads to an expression of this form, we normally solve the equation, the polynomial. When we solve the polynomial, any answer we get there is what we call eigenvalue. So we say that the solution or root of the characterized polynomial, that is the solution to this when we equate it to 0, is called eigenvalues. So that is that lambda we are talking about, we have been talking about there. It is what we call it is that lambda that is called eigenvalue. Is the value of the solution of the characterized polynomial. So this is how to write eigenvalue. A minus lambda I is equal to 0. So the lambda gives us what we call eigenvalue. If they now say that eigenvector is a column vector. This is what we call column vector. It's in column like this. That is a vertical line. So eigenvector S is a column matrix satisfying this equation A minus lambda I times X equal to 0. So that is eigenvalue. Now let's take an example. Find the eigenvalues and the corresponding eigenvectors of this matrix. So this is how to start. We'll first find the characteristics polynomial, that is A minus lambda I. So it's just, let's find the eigenvalue directly. We'll find the determinant. So, and I've told you, just subtract lambda from this diagonal. So this will be 4 minus lambda minus 2 minus lambda. The rest will still remain. Now we are now finding determinant, and I've just taught you how to find the determinant of this matrix. That is this minus this. So this will become, okay, we equate it to 0. So this will become 4 minus lambda into minus 2 minus lambda, then minus this times this. 1 times minus 5, that is minus 5, is equal to 0. So there are 2 minus there to make this place to be plus. So we now need to expand this and simplify. So let's expand this times this, that is minus 8. 4 times minus lambda, that is minus 4 lambda, minus lambda times minus 2, that is plus 2 lambda, minus lambda times minus lambda, that is plus lambda square, plus 5 equal to 0. So if you simplify further, it will become lambda square minus 2 lambda minus 3 is equal to 0. So this one leads to quadratic equation. So we'll now solve the quadratic equation. When we solve the quadratic equation, we have that our lambda is equal to 1 or lambda is equal to 3. So the eigenvalues are now lambda is equal to minus 1, lambda is equal to 3. So we have found the eigenvalues. The question says we should find the corresponding eigenvectors. So since we have known the eigenvalue, it will now be very easy for us to know the eigenvectors. I will now use the formula. The formula for eigenvector is this: A minus lambda I times X is our eigenvectors. Now let's consider equal to 0. So let's consider this. A minus lambda, in fact we have gotten that here, this is it. We'll come back to this place. 4 minus lambda minus 5, 1 and this, 1 and minus 2 minus lambda times this one is this times X. Since this thing is 2 by 2 matrix, you just write that capital letter S as S1, S2, because there are just two things. There is a column matrix. If it is 3 by 3, I will write it to S3. Then we say is equal to 0 times 0. So you keep this one. This is what we are going to use to find our eigenvector. So our aim is now to find the value of S1 and S2. So I will use lambda to find it. I will start like this. I will say that if lambda is equal to -1, because we have found the value of lambda, it is this value of lambda you are going to use to find S1 and S2. If lambda is equal to -1, so in this place, anywhere you see lambda, you put it as -1. You know, this one will become 4 minus -1. That will become 4 plus 1 -5, 1 -2 -1. Because our lambda is -1, it will become plus S1 S2 equal to 0 0. So if you simplify further, you see that this will be 5 minus 5, 1 minus 1, x1 x2 equal to 0 0. Now when we get to this place, these two matrices are these two lines are the same thing. This is 1 and 1, so you make use of any of the two. You cannot make use of the two. You multiply the matrix, that is row by column. You say this 5 times 1 times plus -5 times S2, 5 times S1 minus 5 times S2, or 1 times S1 minus 1 times S2. You use row to multiply. That is multiplication of matrices. So this one will become 5x1 minus 5x2 equal to 0. From this place, you see that 5s1 is equal to 5x2, therefore s1 is equal to s2. In this case of eigenvalue, we cannot find the exact value of s1 and s2. So our aim is just to find the relationship between them. So we have said here that our s is s1, s2. Then we write it back. s1, s2. You see that s2 is same thing as s1. S1 is common, so our answer is 1, 1. Or when you get to this place, you can do it like this. When you get to this place, S2 will be the coefficient of S1, while S1 will be the coefficient of S2. So in that case, S1 is equal to whatever we have here, which is 1. S2 will be whatever you have here, which is also 1. So in that case, you can see this is 1 and 1. So in that case, our answer is our eigenvector. The first eigenvector is 1, 1. So that's our eigenvector. Now, I will now make use of lambda when lambda is 3. So when lambda is 3, this is what I will be using. This one that I wrote as equation 1, I will put 3 here. So this will be 4 minus 3 minus 2 minus 3. So this will give me, if I put 4 minus 3 there, I will have 1. There's -5. There's 1 here. Then -2 minus 3 will become -5. There is x1, x2. So they will always be the same thing, just like this one. They are the same thing. So I will only use one. So I will use this times this times this. So this will become 1 times x1 minus 5 times s2 equal to 0. From this place, you see that s1 is equal to 5 s2. So from this place, we can find our s1 and s2. So I told you s1 will be the coefficient of s2, that is whatever that is here, which is 5. While s2 will be coefficient of s1, whatever that is here. So that one is 1. So we have known s1, we have known s2. So the second eigenvalue will be written in this format. So this will be s1, s2, and our s1 is 5. So this is the corresponding eigenvector. So we have used the second eigenvalue to get the second eigenvector. Let's take another example for better understanding. Find the eigenvalue and the corresponding eigenvectors of this matrix. So this is what we are going to find directly. A minus lambda I is equal to 0. So that is, you just subtract lambda from this diagonal. So this will be minus 5 minus lambda 6 minus 3 4 minus lambda equal to 0. Then we now need to solve. We now need to find the determinant. How do we find the determinant? You multiply these two. That is minus 5 minus lambda into 4 minus lambda minus 6 times minus 3 is minus 18 equal to 0. So it will make this place to be plus. From that place, I can expand. This will be minus 20 minus 5 times minus lambda, that is plus 5 lambda, minus lambda times 4, minus 4 lambda, minus lambda times minus lambda, plus lambda square, plus 18 equal to 0. Then we need to simplify. When we simplify, if you have lambda square plus lambda minus 2 equal to 0. So this is the required equation. So to find the eigenvalues, we solve this quadratic equation. When we solve the quadratic equation, we are going to have that lambda is 1 or lambda is minus 2. Therefore, the eigenvalues are 1 and minus 2. Now, we are now finding the eigenvectors. So the eigenvectors will be this. X, I will write it as S1, S2 is our eigenvector. Then I will use the formula A minus lambda I times X equal to 0. From the definition of, you can rewind and check the definition of eigenvector. And this one is already given there, it's already found in this place. We just need to rewrite this out as this: minus 5 minus lambda 6 minus 3 4 minus lambda, then times x. This is how you are going to write your x: s1 s2, x1 s2 equal to 0. So this is what I'll be using to get my equation. So the first thing is, I'll use the first lambda. I got my first lambda to be 1. So anywhere I see lambda here, I'll put it as 1. So this will now implies, if lambda is 1 here, we are going to have minus 5 minus 1, that is minus 6. And 6, this will be minus 3. 4 minus 1, that is 3. S1, S2 equal to 0, 0. I have told you that they always be the same thing. So you don't need to use the two. You can use any of the two lines, either this one or these two. So I'll use minus 6 and 6. The first one is okay. I don't need to bother myself. So the first one will be 6 minus 6 times S1 plus 6 times S2 equal to 0. From this place, you see that minus 6s1 is equal to minus 6s2. If I bring minus 6 plus this to the other side, from that place, minus 6 cancel minus 6. Therefore, my s1 is equal to s2. From this place, I can know the value of s1 and s2. Therefore, I told you s1 will be the coefficient of what is here, which is 1. S2 will be coefficient of whatever that is here, which is still 1. So I've known my S1 to be 1 and 1. So the first eigenvalue is S1, S2. So that is 1 and 1. So this is the eigenvector, the first eigenvector. And the second case, for lambda equal to minus 2, that's the second answer that we got here. So for lambda equal to minus 2, so this is what I'll be using. Anywhere I see lambda, I'll put it as minus 2. And this, there's minus here before, it will become plus. So what we are going to have there is minus 5 minus 2, that will be plus 2. Then minus 3 is here. 6 is here. 4 minus minus 2, that will be for 2. S1 S2 equal to 0 0. So this will give me minus 3 6 minus 3 6. You will see that they are the same thing, just like the above two. Just like these two, they are the same thing. So we can use if any one of the two. That will be minus 3 S1 plus 6 S2 equal to 0. If you transfer this one to the other side, we have 6S2 is equal to 3. It will be equal to 3S1. This cancel this. Therefore, S1 is equal to 2S2. From that place, I can see that my S1 is equal to 2. The coefficient of this, my S2 is equal to 1. So, my second eigenvector, which is S1, S2, will be equal to, my S1 is 2. I'll put it there. S1, S2 is 1. So, that is the eigenvector. Let's take another example. So, example 3. Given that a square plus this equal to 0, show that A has an inverse if A is this. Hence, find the values of P and Q, this P and Q, and hence obtain the inverse of A raised to power minus 1. Now, this is one of the applications of eigenvalues. We can use eigenvalues to find the inverse of a matrix, either 2 by 2, 3 by 3, or any. So far we can find the eigenvalues easily. So it is very easy for us. But in this case, we don't even need the eigenvalues. The characteristics polynomial is enough for us to do this. We don't need to even find the eigenvalues. But the characteristics polynomial will help us. Now, given that this is this, we ask, the first thing says we should show that A has an inverse. If they say that A has an inverse, we should show that A has an inverse. We need to show that the determinant is not equal to 0. If we can show that the determinant is not equal to 0, we have shown that A has an inverse. So let's find it. Because if the determinant of a matrix is 0, then the matrix is not invertible. That is, the matrix, we cannot find the inverse of such matrix. Now let's find the determinant. This times this, that is minus 3. This times this, that is minus 1 times minus 4, minus 4. This will become plus. That is minus 3 plus 4. This is 1. So 1 is not equal to 0. So therefore, we can say that A has an inverse. You write it there, you write the statement, since the determinant of A is not equal to 0. So it has an inverse. So we are now asked to find the value of P and Q. So let's consider this. Let's consider this. A minus lambda there will become minus 1 minus lambda minus 4, 1, 3 minus lambda equal to 0. Now if you find the determinant, it will give me minus 1 minus lambda into 3 minus lambda minus this times this. That will become minus 4. It will become plus equal to 0. Now we need to expand this and simplify. When we expand and simplify, we should have lambda square minus 2 lambda plus 1 equal to 0. Where we are here, let's take a theorem. So this is a theorem. The theorem says, the theorem is called Cali and Milton theorem. Cali and Milton theorem. The theorem says that every square matrix satisfies its characteristics equation. That is, this is the characteristics equation here. What this Cali and Milton theorem says is that with the help of this Cali and Milton theorem, I can turn this lambda to A. With the help of Cali and Milton theorem, I can turn this lambda to A. That is, this A satisfies this. This A we are talking about here is a square matrix. It satisfies its characteristics equation. So what we are saying by Cali and Milton theorem, so we cannot say that by Cali and Milton theorem, that lambda square minus 2 lambda plus 1 equal to 0 that we got can become or implies a square minus 2a plus 1 equal to 0. If not by that Cali and Milton theorem, we cannot turn the lambda to a. You know, lambda is the eigenvalue, but Cali and Milton theorem says that a can also, we can turn this lambda to a. So we have this relationship from this given matrix. But the given matrix satisfies what is there too. A square plus PA. The given matrix. Now we compare. We compare to A squared plus PA plus QI equal to 0. If you compare it, so this is A squared, A squared. Coefficient of A here is P and A here is minus 2. Therefore, P will be minus 2. And the constant term here is Q. The constant term here is 1. So Q is 1. So we have found the value of P and Q. Here we have been told to find the value of P and Q. So with the help of eigenvalue and Cali and Milton theorem, we are able to find the value of P and Q easily without stressing ourselves. Now we are now asked to find the A inverse. Let's now find A inverse. From this place, if you make this 1 the subject of formula, here, if you make it the subject of formula, we are going to have 2a minus a squared. This is 1. What we are looking for is A inverse. Let's multiply A inverse to both sides. 1 times A inverse will be 2A. We are multiplying A inverse to both sides. So 1 times A inverse is A inverse. Now by indices, this will cancel this. It will remain ordinary 2 there. Or we can write it as 2i or ordinary 2 minus A squared by indices. 2 minus 1 is 1. So it will be ordinary A. Now therefore our A inverse is ordinary 2. Ordinary 2 means 2, 0, 0, 2 minus A. A is given here. This is our A here. So we substitute the value of A there. Minus 1, minus 4, 1 and 3. Now let's subtract 2 minus minus 1. That is 3. 0 minus minus 4. That is 4. And there 2 minus 1 0 minus 1 is 1 minus 1. 2 minus 3 is minus 1. So this is the inverse of the matrix. So we have used the determinant, where we have used the eigenvalues and Cali and Milton theorem to find the determinant, the inverse of a matrix.